In the last video, I did a few examples of writing different functions using the basic geometric function, geometric series function expansion series. And I'm going to continue with that here. So in the last video, we were looking at cases like, for example, let's say you wanted to model the function 8 over 1 minus x. Hopefully you can notice that that's really just taking 8 times the function 1 over 1 minus x. We know the series representation for 1 over 1 minus x. And so, you can basically take the series 1 plus x squared plus x cubed and so on, and you can just multiply that whole series by 8. And, as a result, you would get 8 plus 8x plus 8x squared plus 8x cubed and so on. It's literally just the function terms multiplied by 8. Or you could say it's the sum from n equals 0 to infinity. It would still be x to the nth power, but the terms would be multiplied by 8. And so again, you'd get x to the 0 power, you'd get 8 as your first term, x to the first power, you'd get 8x to the first, x to the second power, you get 8x squared, and so on, okay? That's if your function's multiplied by a particular value, okay? If you had a function x over 1 minus x, hopefully you would notice, hey look, that is literally just the 1 minus x function multiplied by x. So I'll write out the series, 1 plus x squared plus x cubed and so on. And then I'll just take that whole series and I'll multiply it by x. And that'll give me x plus x squared plus x cubed and so on. And if you wanted to write your series representation for this using summation notation, you could say, well, we're going from n equals 0 to infinity. The original function is x to the n, but we're multiplying each term by an additional x. And so, for example, you could write that as x to the n plus 1 power. So when n is 0, you get x to the first. When n is 1, you get x to the second. When n is 2, you get x to the third, and so on. So one option is that your series got multiplied by something, okay? And again, just each term gets multiplied by that value. Should be relatively straightforward, okay? The second scenario we talked about was cases where you replace the input value in the function with something else, okay? So the function that we're modeling here is 1 over 1 minus x, or as I like to think about it, 1 over 1 minus the input value, okay? So if I wanted to model the function g of x equals 1 over 1 minus 5x, I'm replacing the x with a 5x, okay? I'm really taking f of 5x. I'm inputting a 5x in place of the input there, okay? That's a little bit different, okay? We're not just multiplying each term by 5x. We're putting 5x into the function, okay? So if I was going to model this type of scenario, 1 over 1 minus 5x, instead of x, everywhere where I see an x in this function, I'm going to be putting a 5x because that's what the value being input into the series is. So that would be 1 plus, my input in place of the x would be 5x. My input in place of the x would be 5x. The input is being squared, okay? The input is being cubed, and a 5x would go in place of the input. And so you could write the series this way, and it would continue on out infinitely. You could simplify it. You could write it as 1 plus 5x plus 25x squared plus 125x cubed, and so on. If you were trying to write this using sigma notation, again, sometimes the unsimplified form is going to be easier for people. Sometimes the multiplied out form will be easier for people. But I know that the basic system is x to the n power. I know that I have taken out the x and I've put in a 5x in place of it. So actually you can just take out the x, put in a 5x, and you could write this as 5x raised to the n power. So 5x to the 0 is 1, 5x to the first is 5x, 5x squared is 25x squared, 5x cubed is 125x cubed, and so on. Okay, so again, the series didn't get multiplied by 5. 5 got put in for the x, and we're getting a series that looks like that. And again, some of you might notice the same pattern down here. This could also be written as 5 to the n times x to the n, if you wanted to write it in that form. And you might notice that more if you had it written the second way. It just kind of depends on how you set it up. Okay, now I could go a step farther. I could do the function Let's say I wanted to do x over 1 minus 5 of the x. So you look back here and you say, okay, 5x got put in as my input. That would give me this. And then the series 1 over 1 minus 5x got multiplied by x. So this whole series, each term would get multiplied by an additional x. And that would give me x plus 5x squared plus 25x cubed plus 125x to the fourth, and so on. Okay, so you still have powers of 5, but each of your x exponents is one larger than it was supposed to be originally. So you could do something like this. You could say, well, that's the sum from 0 to infinity of, okay, so our 5s are all being taken to the n power. Our x's are all being taken to the n plus 1 power. Or actually, you could have done it the other way. You could have said, I'm taking 5x to the n power, but each term is getting multiplied by x on the outside. And when you simplify that, that's 5 to the n times x to the n times an additional x. You can add your two exponents there, and that ends up being 5 to the n times x to the n plus 1, okay? Maybe something like that. So 5 to the n times x to the n plus 1. So when n is equal to 0, you're going to get 1, but you're going to get x to the first. When x is equal to 1, you're going to get 5, but you're going to get an x to the second. When x is equal to 2, you're going to get 25, but you're going to get an x to the third. So again, you've got multiple things. The series can be multiplied by something. You could replace the input value with something. Different things can possibly occur. Okay? Now let's take a look at a few more examples. So let's say that I had a function g of x is equal to 1 minus 1 over x, 1 over 1 minus x squared. Okay? I notice that this looks a whole lot like this, okay? It's still 1 over 1 minus something, okay? The difference is, instead of an x, I have an x squared as my input, okay? So same kind of thing. You're just going to write out the original series, and you're just going to replace every x with an x squared. I'm replacing the input. I'm replacing the variable with an x squared. So I have my first term plus my input to the first power, and my input here is going to be x squared, plus my input to the second power, and my input is going to be x squared, plus my input to the third power, and so on. And that's going to end up being 1 plus x squared plus x to the fourth plus x to the sixth, and so on. Okay? Notice the powers of x are increasing by 2 each time. All right? So if you wanted to write the series representation of this, you could go from 0 to infinity. You might notice that it's the same pattern we had before. It was x to the n. Now we have an x squared in place of the x, and it's being taken to the n power. Or some of you might notice this is x to the 0, x to the second, x to the fourth, x to the sixth, and so on. You might notice that the basically the term number is doubling each time. That's the same thing as x to the 2n, right? If n starts at 0, it goes to infinity. So you start out x to the 0 is 1. X to the 2 times 1 is x squared. If x is 2, you get an x to the fourth, and so on. And by the way, that follows this, right? Because power to a power, you multiply your exponents. So if you have anything of the form 1 minus some kind of an input, you should just be able to replace your x value with that. Okay? If it was 5 over 1 minus x squared, that would be this whole series multiplied by 5, and you just have a sum of 5x to the 2n, and that would happen as well. So hopefully we're seeing those two things. Your function can be multiplied by something, but you can also replace the input with something. All right, so there's some tougher examples that will also work. Let me just show you one of these. So it's not always going to be 1 over 1 minus something. It could be 1 over 1 plus something. Okay, and on the surface you look at this and you say, well, you know, it's got to be a subtraction there. You know, I guess we're out of luck in this case. Okay, but if you can rewrite it into a form 1 over 1 minus something, you should still be able to make this work. So minus a negative is the same thing as a plus, right? So it's 1 over 1 minus the input, 1 over 1 minus the input. I'm just going to put a negative x into my series in place of x. And take a look what happens. Something very important happens here. So I've got 1 plus, I have negative x going in place of x. I have negative x going in place of x and then being squared. I have negative x going in place of x and then being cubed, and so on. If you simplify this, something very interesting happens. Remember, even powers of negative numbers become positive. Negative powers of negatives stay negative. So you're going to get 1 minus x plus x squared minus x cubed plus x to the 4th, and so on. It's called an alternating series, which I think we've already worked with. Your signs are going back and forth, okay? And this can be handled a couple different ways. If you're trying to write this using sigma notation, you could just say, instead of x to the n, I'm going to do negative x to the n, and you'll get negative x to the 0, which is 1, and you'll get negative x to the first, which is this, and negative x to the second, which is that, and so on. A lot of times people factor out the negative 1, okay? This is really negative 1x to the n. So negative 1 is being taken to the n, and x is being taken to the n. A lot of people are going to write this as the sum from n equals 0 to infinity of negative 1 to the n times x to the n. And so what will happen is, when n is even, you get a positive. So when n is 0, you get a positive. When n is 2, you're going to get a positive. When n is 4, you get a positive. Meanwhile, when n is 1, you're going to get a negative. When n is 3, you're going to end up getting a negative, and so on. So most people would probably write this like that, all right? And if you wanted something like x over 1 plus x, you could take this whole series and you could multiply each term by x. It would just raise all your powers of x by 1. And so maybe you could have negative x to the n times x to the n plus 1. You know, maybe something kind of like that, okay? Let's do one more that's maybe kind of complicated, maybe 2 more. Okay, so let's say we have an original function that is 3 over 1 plus x to the 4th power. Okay, something like that. So we've got a couple of issues here. First of all, it's supposed to be 1 over 1 minus x. We've got a 3 up here. Okay, so you should be able to just factor out that 3 and write it as 3 times 1 over 1 plus x to the 4th power. Okay, so that's one thing. Okay, second of all, it's supposed to be 1 over 1 minus the input. Here it's 1 over 1 plus the input. So remember, you can write this as minus a negative x to the 4th. Okay, so we're going to take 3 times our final series. Our input for the series, instead of being x, is going to be a negative x to the 4th. Okay, and that's what we're going to substitute in. So as a series, what would that look like? Well, first of all, the whole series is going to be multiplied by 3. So I think I'll put a 3 out here in front. And then we're going to have 1 plus the input to the 1st power. And the input here is going to be negative x to the 4th. Okay, plus the input squared. Okay, and the input's going to be negative x to the 4th. Plus the input cubed. And the input's going to be negative x to the 4th, okay? And so this is going to be 1 minus x to the 4th plus x to the 8th minus x to the 12th, and so on. Each of the terms is going to be multiplied by 3. So we'll have 3 minus 3x to the 4th plus 3x to the 8th minus 3x to the 12th, and so on. And again, sometimes you might find this easier to use to write the general term of the series. Sometimes it might be easier to pick up on your pattern here. What's really happening here? Well, first of all, each term got multiplied by 3, so we're going to have a 3 out in front. You have powers of x to the 4th being taken to the n power. And remember, it's got to alternate. So you could say you're going to have negative x to the 4th to the n, or you could break this up as a negative 1 x to the 4th to the n, and you could rewrite that as we're going to have our 3 here. We're going to have a negative 1 being taken to the n, and then we're going to have an x to the fourth being taken to an n, is probably how I would write it. Or you could write this as x to the 4n power would also work there. It's probably the best way to write that. We'll write it in that form. So that's how I'd probably write it. And again, I would always check at the end to make sure it works. Okay? So this is from n equals 0 to infinity. When n is equal to 0, that's going to be 1. When n is equal to 0, that's going to be 1. So you get 3. When n is equal to 1, you get a negative 1 here. You'll get an x to the fourth. There we go. When n is equal to 2, you're going to get a positive 1. You're going to get an x to the 8th. When n is equal to 3, you're going to get a negative 1. You're going to get an x to the 12th. And you can see that your series works out. All right? So that's kind of the basic idea. All right, let's try, now let's try one more. Oh, this would be interesting. Okay, let's try g of x equals, let's try x squared over 1 minus 3x squared. No, let's just do minus x squared. Let's do minus x squared. Okay, I haven't done anything like this yet. Okay, so a couple of things here. This is really this function here multiplied by x squared. Okay, so we have an x squared times 1 over 1 minus x squared. Okay, would be another way of writing this. And we can see that this is very close to this. There's a minus x squared at the end, which seems a little weird. We'll have to figure out what's going on with that later. All right, so this is really 1 over 1 minus an input of x squared instead of 1 over 1 minus an input of x. So we should just be able to put an x squared in as our input there, and that should work out fine. So that series is going to be 1 plus, instead of x, we're going to have an x squared, so x squared, plus, instead of x, we're going to have an x squared being squared, that'll be an x to the fourth, plus our input cubed. Our input here is x squared, okay? So that's going to be the starting part. The whole thing is getting multiplied by x squared, okay? So our series is going to continue. Each term is getting multiplied by x squared. So what's that going to give me? That's going to give me x squared plus x squared times x squared is x to the fourth, plus this is going to be x to the fourth times x squared. That's an x to the sixth, okay? Plus that's going to be x squared to the third, which is x to the sixth, then we get an x to the eighth, and so on. Okay, there's our series. And then notice, we've taken care of all of this. It says I'm supposed to subtract x squared here. Well, that's just one term of the series. I'm just going to subtract x squared, and we're going to be left with x to the fourth plus x to the sixth plus x to the eighth, and so on. And that's all that's going on. And if you notice, this is actually a pretty simple pattern. This is just even powers of x. So you could write this a couple of different ways if you were trying to write kind of the general series formula for this. You should just be able to do something kind of like the sum from 0 to infinity. You could do an x to the 2n. And the difference here is we want the series to start at x to the fourth. So you could do a couple things. You could go from 2 to infinity, and it would start out at x to the fourth, and then you get an x to the sixth, and so on. If you wanted to start it out at 0, since we've usually been starting out by 0, the other thing you could do here is you'd like to start it at the fourth power instead of the 0 power, so you could do like an x to the 2n plus 4. So when n is 0, you get x to the fourth. When n is equal to 1, you're going to get x to the sixth. When x is equal to 2, you're going to get x to the eighth, and so on. So there are different ways you can kind of tweak things as you try to write your series representations. But that's the basic idea. So hopefully that's helpful. It can be a little bit tricky, but again, it's really a lot of algebra, not a lot of calculus, not really any calculus going on here. So hope that gives you enough to go on in the example problems in this set.